Golden ratio. Why is it irrational? Imagine a number so special that it appears in art, architecture, and nature, yet it cannot be written as a simple fraction. That number is the golden ratio, often called phi. It has fascinated mathematicians and artists for centuries. But why is it considered irrational? Let's find out. The golden ratio, represented by the Greek letter phi, is about 1.618,033 digits repeating. It's called irrational because it cannot be written as a fraction of to whole numbers. This means its decimal goes on forever without repeating. Unlike fractions like 1/2 or 3/4, phi's decimal pattern never settles into a pattern. It keeps going endlessly. Phi is the positive solution to a quadratic equation. That equation is phi squared minus phi minus 1 equals 0. When you solve it, you get phi equals 1 plus the square root of 5 divided by 2. Since the square root of 5 is an irrational number, phi itself must be irrational. You can't turn it into a simple fraction because of this square root. Now, let's look at how phi relates to shapes like the regular pentagon. The ratio of a pentagon's diagonal to its side length is exactly phi. If phi were a rational number, it could be written as a fraction. But when you analyze the triangles inside the pentagon, you find contradictions that prove phi cannot be a fraction. This geometric proof confirms phi's irrationality. Another interesting fact is that phi is called the most irrational number. This means it's the hardest irrational number to approximate with fractions. Its continued fraction representation is very simple and uniform, with all partial denominators equal to 1. Because of this, rational approximations of phi converge very slowly. It's like trying to pin down a moving target. This extreme irrationality has real-world effects. For example, in systems where different frequencies need to stay out of sync, ratios involving phi prevent resonance. This is why phi appears in natural arrangements like sunflower seeds or pine cone scales, where it helps optimize packing and growth. In the world of number sequences, phi appears naturally as the limit of the ratio of consecutive Fibonacci numbers. As you go further along the sequence, the ratio gets closer and closer to phi. This connection shows how phi links patterns in mathematics to patterns in nature, making it a truly remarkable number. So, in summary, the golden ratio is irrational because it solves an equation involving the square root of 5, which is irrational. Its unique properties make it stand out among numbers, especially in how difficult it is to approximate with fractions. This special trait helps explain why phi is so important in math, science, and the natural world.